Welcome to the Conference of Movements 26 Virtual, COM26V.com. This is the second day of our conference. The first day was celebrating Indigenous Heritage Month. And today we're talking about climate change and the solutions for climate change. So we have here today the team from the MEER project, and is led by Yi Tao, who's a PhD from Harvard University, the Rowland Institute at the Harvard University. And also with us is Gregory Pan from the Cornell University, and Washinga Roy. Hopefully I pronounced it right. Maybe you can correct me. It was a little bit difficult to pronounce. She's a senior at Emory University in environmental sciences, but you can each introduce yourself a little bit more clearly. If I misspell your name, said your name wrong, please correct me. So thank you so much. Yi Tao, would you like to talk a little bit about your background? Then afterwards, we'll go to Gregory and Washinga.
Okay, hi everybody. So thanks for the invitation. It's a little bit on short notice, so we just pulled together some slides and maybe some ideas to share with you in the past 20 minutes or so. But anyways, so a little correction. So my PhD is actually from MIT, and most of my research work was actually carried out at ETH Zurich. So I was trained as a multidisciplinary engineering scientist. And when I was hired by the Rowland Institute at Harvard 4 years ago now, my mandate was to develop a atomic resolution microscope that can give you three-dimensional images and structure of heterogeneous pieces of matter to, for example, get the structure of proteins or antibodies or other nanoparticles. So that was my original interest. But really, the climate emergency has compelled me to leverage my learning and my skills to also help at this effort. It's a little bit like, everybody's trying to find solutions for COVID these days. So as an engineering scientist, I think the climate mitigation field need people with such training to have a different perspective. So today, hopefully, we'll be able to provide such perspective, really zoom out from what's happening around us and take a top-down and also bottom-up view of the Earth system, and really to get to the root cause of our ailments and find the most efficient method, engineering and otherwise, to solve this issue. So we're excited to share some ideas and have a discussion.
Thank you so much for joining us. So Gregory, would you like to introduce yourself?
Hi, I'm Gregory Pan. I'm a junior studying environment and sustainability at Cornell. And my role in this team is I'm the urban built environment project lead. So what our project has been doing, our section of the project has been doing, is focusing on developing technologies and system infrastructure, energy system infrastructure to be more efficient in the residential sector.
Thank you so much. And the third person, I don't want to pronounce your name wrong.
That's okay.
Your name, right?
Hi, my name is Rashida Roy. I'm a current senior at Emory University studying environmental science and chemistry. And I am a member of the ocean deacidification team for Project MEER Reflection. And our mission is to develop a strategy for solar thermal ocean liming as a way to target ocean acidification as well as carbon sequestration. And we are assessing the biological and engineering perspectives while in this process.
Thank you so much. Would you like to begin your presentation?
All right, let's get it started and see where it goes. All right, I hope I'm sharing the right screen. David, could you please confirm?
See the screen.
All right. All right, so just a few words about the Roland Institute, where I work and where this project was developed. So it's this building on the right, the brick building. It was constructed in the 80s and was funded by the same gentleman, the late Dr. Edwin H. Land, the founder of Polaroid Corporation. And he was a Harvard undergrad for a year and then quit school and started his research and company. And he was very much into education so today Harvard Science Center is a testament to his devotion to undergraduate research. And at the Roland Institute, we are developing like really cutting edge instrumentation to do a range of measurements and new studies on the neurons, for example. And also in my lab, we're looking at the nanoscale and now the ultra large scale of climate. And each fellow, we hire about 2 each year. We're given 5 years of essentially unlimited funding to look at whatever problem that we judge to be important to solve in the world. So I like to conceptualize different scientific and engineering endeavors on a two-dimensional plane. You will see that in this presentation, we like to conceptualize things this way to really make them clear. So we, as scientists, we study stuff of different sizes, as small as molecules and as large as people, and also galaxies and planets. So before I joined, we had a pretty good coverage of a wide range of topics, and also topics that of different level of complexity in interaction of different parts in that problem. And recently, we have added what we call civilizational habitat engineering to the list. Because in year 2020, we think it's very important to tackle the ongoing climate catastrophe. So we are thinking about methods to preserve habitat for a human on this planet so that we can do all the great things that we know the species is capable of. So in my lab, we have traditionally taken a target-driven approach to developing science and engineering. We find that when you have a specific grand target, however difficult, it will stimulate the development of new tools to reach such goal. And in the process of developing new tools, one invariably finds new science that's interesting. So it's a quite fruitful and efficient way to conduct fundamental research. So my original, let's say, interest when I was hired here a few years ago was to build a microscope that could give you atomic resolution structure of any heterogeneous speck of matter. And this quite difficult challenge have led to a range of results ranging from like the fabrication of nanomechanical resonators from single crystal diamond that's very, very small and sensitive to forces, to a very recent result of machining, subtractive machining with basically atomic resolution in depth. So that's a world record. We're still in the process of developing and understanding the mechanism behind this process. But a few years back, it became clear that we cannot really just focus on these small-scale engineering efforts, but we need to look around what's happening in the world around us. So we have these extreme events, certainly accelerated by increasing temperatures and reducing humidity in soil, of absolutely catastrophic fires going around. So it appears to us that we should draw another two-dimensional graph, but this time illustrating the different threats that's threatening our civilization and also our species. So in this plot, we're plotting several of the well-known threats, from ocean acidification to sea level rise to ocean plastics, air pollution, and a range of downstream consequences of thermal extremes. So we plot them. On the x-axis it's the urgency. Basically, the more urgent they are, the more they are to the right side. And on the y-axis, we plot the severity of these threats if they are fully materialized. So oftentimes when we talk about climate change, we tend to focus on sea level rise. Maybe it's a consequence of just how the media has been talking about it. But compared to other threats that we'll be talking about, it's a relatively minor one because it's happening at the interface between ocean and land. So it's happening along a line. In comparison, for example, the ocean acidification problem is potentially much more serious one because it's impacting the whole volume of the entire ocean on the planet. And there will be a certain point if we were to continue emissions and suppose civilization were to continue somehow at the current rate of CO2 injection into the oceans, by the end of the century and somewhat beyond there, many portion of the ocean will be simply too acidic to support many types of organisms, calcifying organisms. So that will certainly have a much larger impact by itself compared to just inundating human cities around coast. We can move inland, but we cannot continue to have aquaculture or fisheries alive when the full impact of ocean acidification hits. So today, later on, Rashija will tell you a scheme that we developed that allows for deacidifying the ocean and at the same time provide vital energies for human civilization. Another point I like to point out is ocean plastics. So it's very much at heart for many climate activists and the environmentalists. But if one really delved into the literature, there is no conclusive evidence of substantial toxicity for humans. And that's not true for air pollution, for example, for which there is abundant evidence of health risks. However, there are still people living under those conditions. They have reduced, while they have reduced life expectancy, those societies are still developing economically. So it's not a threat that has the potential to collapse our civilization. The elephant in the room are thermal stresses that can, and temperature extremes that can precipitate other ailments, including pests like the locusts that we've been witnessing this past year. And the most vulnerable system that we rely on is the food system. And there's increasing evidence that food production will shrink on the order of between 5 to some cases 50% from now until a few decades from now if we were to continue on the current trajectory of temperature increase. So in summary, we really need, first and foremost, target the thermal threat and then leverage infrastructure that we build for targeting this threat to then address subsequent ones, including ocean acidification and air pollution. So today, unfortunately, due to the short notice, we do not have the team members who work on those problems with us. But if you're interested, please contact us, and we're happy to tell you more about it individually. So basically, from my point of view as a researcher, I'm very much interested in this three-dimensional microscope, but the objective fact of the current situation in 2020 behooves us to really switch focus to look at the more urgent need to maintain habitability for humans for the next decades. And we find that in order to do that, nobody can do it alone. So we need to educate the public. We need to train new students. That's why I also have a passion for teaching and mentoring. And today you'll hear from two of the members who have joined our project since earlier this year. And they have learned a lot and really contributed greatly to developing the project. So, so today we'll have a few objectives. First of all, let's talk about how urgent the climate crisis really is. And then we need to discuss why renewable energies alone will not be a solution, given the complexity of the Earth system that we will try to explain as well. And then we will discuss about the solution framework, and then discuss why it's important to first get temperature under control before contemplating drawing down CO2 from a well-mixed atmosphere. So here I'm plotting some data points since we started to burn fossil fuel as humans, and how we have moved the entire Earth system in this conceptual two-dimensional graph, where the x-axis is the atmospheric CO2 concentration in ppm, and the y-axis is the global average surface temperature. So I'm color-coding the data point, in this case, in logarithmically. So we plot as far back as roughly 270 years ago, 1750 roughly, and until the present day. And we can see that we're moving the system steadily along a trajectory. And if we simply use linear extrapolation of that trajectory, which historically has been pretty good at explaining historical data, we project that we're basically going to cross the 2 degrees Celsius with respect to 1750 pre-industrial baseline within the next 2 decades. And that has a very unfortunate consequences, as we will now explain. So this way of looking at climate change is not very common in the field of climate change discussions and mitigation. Usually, I want to point out that we usually see time on the x-axis. And I would argue that is not a very efficient way to really understand the problem, because first of all, time is a human construct. And we are really worried about the future because we have the capacity to think beyond the present day. But climate change will eventually impact us through the effect on the food and the environment that we depend on. And the food, like plants and animals we depend on, they care more about their immediate surroundings, the wet bulb temperature, if there's a drought, if there's a fire, if there's sufficient rainfall and fertilizer for them to grow. So what we should focus on instead in trying to really understand the impact of climate change is to look at the parameter space, the physical parameter space. So plot trajectories and data in these spaces. And this temperature CO2 graph is one such example. Okay, so enough for the detour. Now let's come back to this particular graph. So I have a region plotted green. This region is what available data seems to indicate to be a safe region for the ecosystems and the animals and plants that's living on this planet. And how did we get to this region? First of all, we know that plants need CO2 in the air in order to do photosynthesis. They need to take in carbon dioxide through their stomata in order to reduce them and then make them into sugars. If there's no CO2, then they cannot have the starting material for their growth. So we need at least 30 to 50 ppm. On the higher end, we know that through extensive experimentation, that plants and both in ocean and on land start to experience toxicity effect from CO2 when the concentration goes beyond 1,000 to 2,000 parts per million. Okay, so we have boundaries on the x-axis that we shouldn't surpass. On the temperature axis, the limitations are even more severe. So we have different studies that basically show even 1 degree Celsius rise is sufficient to induce quite negative reduction in longevity and fertility for many species. And the 2 degree Celsius rise has been uniformly shown to be detrimental for experimental systems that scientists have looked at. So the +1 is a review of such studies. And at 3 degrees above pre-industrial, ecologists are screaming for biological annihilation. So it's certainly not a territory we want to venture towards. So the analysis on the previous screen shows that let's just suppose we can decouple, separate the CO2 and the temperature as two separate independent variables, we are already on our way to hit our head against the thermal boundary in the next 10 to 20 years. Whereas the intrinsic toxicity effect of CO2 is still over a century away, even on current trajectory. And we actually cannot actually get there even if we burned all the fossil fuel reserve. So that really puts into perspective the fact that it's a thermal stress that we need to target, not greenhouse gas, including CO2 per se. Now we're ready to explain why renewable energies are not solutions and why focusing on them and asking exclusively to get rid of fossil fuels is actually deadly. And it's really an addiction, the withdrawal symptoms of which are not something that we can take without substantial and deadly consequences for our current civilization. When we burn coal, as you saw on the previous slide, we emit a lot of smoke, which contain different compounds, including unburnt volatile organic carbons, and also sulfur oxides and nitrogen oxides. These compounds, they undergo complex reactions in the atmosphere driven by sunlight to produce nanoparticles that can actually cool the Earth by several mechanisms. One is that they directly can scatter light and send some of the incoming shortwave radiation back into space. They can also act as condensation nuclei to promote cloud formation. And that's the basis for some geoengineering concepts like marine cloud brining that we'll be discussing later. But the important thing to understand is that because we're constantly emitting these aerosols and their precursors, right now we have about 1 to 2 watt per meter squared of cooling on Earth everywhere, averaged everywhere over the Earth's surface, based on this particular study. And a more recent review of all of the literature in the past 40 years constrains that number to 1.2 plus minus 0.8 watt per meter squared. So that's quite substantial. It's like a LED lit at every square meter of Earth. Now, let's ask the question, what happens when we were to clean this thing out? Or equivalently, what happens if we stop to burn fossil fuels globally tomorrow? How much heating would that cause? So I'm an experimentalist by training, and I like to look at historical data and ask Earth that question. So Dr. Schneider last year really did a very exhaustive study of the Earth's historical climate and its dependence on the effective forcing in watts per meter squared. And for the region that we're concerned with, the slope is roughly 0.8 degrees Celsius per watt per meter squared of forcing. And very recently, we have newer papers coming out, basically giving comparable values, but actually slightly higher. And because we have to remember, so this value of 0.95 plus minus 0.3 degree per watt meter squared is based on the assumption of doubling of CO2. It's a metric that climate scientists like to use. But we need to remember that we have not yet doubled CO2, and that at the lower ends, there's actually a higher sensitivity because there's a saturation effect at really, really high CO2 concentrations. When you have, infinitely high CO2 concentration, then you would have, saturated all the absorption bands, then any additional increase wouldn't add much. So there's a decreasing sensitivity with increasing CO2. And right now, the relevant number to take is roughly 1 degree Celsius per watt per meter squared. And these are pretty convenient numbers. So to answer the question of how much the Earth will warm, after we stop to burn fossil fuel, we take the sensitivity number, roughly 1 degree per meter squared, a watt per watt per meter squared, multiplied by 1.2 plus minus 0.8 watt per meter squared. And we roughly get a number of 1.3, 1.5-ish. So that means if we were to lose fossil fuels, then we're looking at a doubling of the heating that we have actually realized in the system. And that would be quite catastrophic for ecosystems and agriculture globally. And there's abundant literature that I invite everybody watching this to go check for themselves to really check the robustness of this physics. That's very well understood, at least the sign of it. And just to give a illustration of this effect, so this is very new data coming out of the Netherlands. So after Western Europe went into lockdown, there's a substantial reduction in emissions, and as a result of that, scientists measured an increase in direct irradiance, basically sunlight that can immediately go down from the sun to the ground without being scattered, with respect to sunlight that has to be bounced off of some aerosols and then strike the ground at an angle. So compared to before we stopped, before we started the lockdown in Europe to afterwards, there's a clear increase in the proportion of direct irradiance. In addition, there's also an increase in the total amount of sunlight received on the ground, at least at this measuring station in the Netherlands. And the amount of sunlight they got this year as results, likely linked to this shutdown of emissions, is the highest since 1928. So that's something to keep in mind. And the value was about 2 watt per meter squared, higher than previous values. All right, so now we are ready to explain why, even if we could magically transition to 100% renewables today, it's not sufficient to really ensure safety for the world. What would so in this graph, I'm plotting hypothetical scenarios. Let's assume we were to choose just any one of a particular renewable energy. But before, let's look at what happens if we were to continue on current course. If we were to continue burning fossil fuel, it doesn't look good at all. We will be slowly but surely gonna cross all the limits that we shouldn't be crossing, and as a consequence, suffer catastrophic damage to our infrastructure and civilization. But if we were instead gonna transition, say, into wind energy as of this year, then we would, within 5 years roughly, lose or actually realize all of the hidden heating that's already in the greenhouse gas that's in the atmosphere as a result of losing this aerosol cooling effect. And based on the latest estimates of uncertainty, the range, we have roughly like 90% confidence it will be between 1.8 to 4.5 degrees Celsius above, compared to pre-industrial choosing 1752 as the baseline. So this number, there may be like 0.3 difference between my preferred definition of 1750 to what the mainstream climate field like to take, somewhere around the 1850 to 1950 range. In my mind, it's more rigorous to use a date before humans really started to burn coal and fossil fuels on a large scale. So I suggest that we stick to the most rigorous possible as scientists, 1750. All right, so all the renewables, regardless of which one, if we were to magically transition, would incur this sort of unfavorable increase, some of which we might be witnessing this year as a result of COVID-19 lockdowns. And subsequent to that, different technologies might continue to contribute happily at much slower pace CO2 emissions as a result of infrastructure maintenance, with some associated heating due to the CO2 equivalent that's emitted. Something I like to draw people's attention to include wind energy. Wind energy, in terms of infrastructure needs, is actually better than the solar alternatives. However, because of its mode of action, it's actually churning up the atmosphere and causing excess heating to land by several mechanisms. One of which is it keeps nighttime temperatures really high because it mixes up the boundary layer, so the land cannot properly give it heat off to the upper atmosphere during the night in the absence of incoming solar radiation. So that has consequences for sustained thermal extremes in the future. So wind may not be a good alternative, despite its relatively lower infrastructural demand. The other point I want to make is that planting trees, if we want to go to bioenergy, then we would need to convert so much high albedo areas into low albedo forests to grow these trees. And the heating absorbed by these dark forests would drive substantial increase of about 3 degrees Celsius just from the heating from the dark leaves. And in addition, we simply do not have land on Earth to implement such forests. So it's not really a viable alternative. So if we were to transition, in the future, which we have to a renewable energy, the only sensible choice is solar thermal, because it's the one that incurs the least infrastructural emissions, and it uses the least energy because it doesn't require, as in the case of solar photovoltaics, the refinement of high quality, high purity silicon metal. So let's now discuss the solution framework. But before, let's take a very simple conceptual view of why we settled on this particular approach. Historically, the amount of heat trapped in the Earth's atmosphere and ocean mix layers have been relatively constant on the timescale of centuries to millennia. That's because we roughly have the same flux of incoming shortwave radiation compared to the net flux of outgoing long-wave radiation measured in energy density units. What happened recently as a result of burning fossil fuel and the emission of greenhouse gases is that we closed the outlet of outgoing long-wave radiation. And as a result, we are in a state of dynamic disequilibrium characterized by increasing amount of trapped heat as a function of time. So in order to reestablish dynamic equilibrium so that we have, again, stable climate, we have two choices. Either we do as most people and people in the field have been trying, increase the outlet by drawing down CO2 gases and eliminating further emissions, or we could also slow down the rate at which shortwave radiation is converted into heat within the Earth's atmosphere and ocean systems. Conceptually, we believe that there's a substantial difference when it comes to the engineering implications. If we want to target outgoing long-wave radiation, what we have to do is to clean the entire atmosphere and the ocean. So by definition, that's three-dimensional volumes that we are tasked with cleaning. So it's a 3D engineering problem. You have to filter the air or, in addition, the ocean water. So there's no escape from tackling a three-dimensional problem. However, if we're just targeting shortwave radiation, we can basically do that using a planar MEER. Even a few nanometers, tens of nanometers of reflective film installed on land will be able to achieve the same effect. So that's a much more manageable engineering problem from a scale requirement and also efficacy over time. So the solution, the bare bones of the solution, can be summarized in this figure for how to really address this temperature parameter. 1 ton of CO2 gives roughly, averaged over the Earth, 3 times 10 to the minus 12 watt per meter squared of forcing. And we can ask the question of how much negative forcing, so in order to compensate this positive forcing by CO2, do we need from the mirrors? And each mirror can roughly reflect back into space on the order of between 2 to 300 watt per meter squared of power density. So we can calculate for the total surface area of Earth what's the average effect of 1 mirror, that's 1 meter squared. And so the answer comes out to be on the same order of magnitude, more or less, compared to 1 ton of CO2, which means we need on the order of 6 to 10 meter squared of a mirror to cancel instantaneously the heating effect of 1 ton of CO2 that's well mixed into the atmosphere. And such a piece of mirror is certainly possible to make for the price of about $10, because one can nowadays buy it online from Alibaba.com for $6 USD, and I'm sure there's profit made in that process. So now this is a slide showing again the idea of different solutions categorized by whether they are targeting the outgoing long-wave radiation, which by default is 3-dimensional problem, versus some solar radiation management techniques, which are can be made into 2-dimensional problems in some cases. So we will not discuss in detail the different merits of the solutions, but these ones are the only ones that are both scalable and can act with sufficient speed to tackle the problem, given the kinetics of the problem. So here are some preliminary data produced by one of our team members, Jagger Alexander, asking the question of where is it best to place, say, horizontal mirrors. And we find that actually in oceans are quite good, subtropical oceans are prime spots because they receive the most sunlight that's perpendicular more or less to the surface. That's what's inspired this conceptual illustration of a array of floating mirrors with the primary purpose of preventing heat absorption by the ocean. And if, let's say, we were to just in the hypothetical case that we were to continue to burn coal from now until end of century, and we were to follow RCP 4.5, then we need to roughly offset 1.5 watts per meter squared of extra heating by that time. And in order to offset that heating, basically to keep the climate by the end of century the same as it is today, we need to cover 1% of Earth's surface from now until then in the next 80 years in order to keep the climate stable. So then we have also other tasks once we can, have a mean to stabilize the climate that Rashida will talk to you about, that I will just skip over now. And I think that's, so before I conclude, I like to highlight that Project MEER reflection is more complex and more comprehensive than it might appear at first glance. So it is true that we're just using the humble mirrors on the ground, or maybe slightly more fancier floating in the ocean. But we're capitalizing on the simple fact that mirrors are nothing but light handling devices. And once you can channel and handle incoming sunlight, which is the ultimate source of renewable energy, then you can envisioning doing a whole bunch of stuff with that source of renewable energy. And we find it's possible to stabilize planetary temperature. We have schemes to couple mirrors, both floating and on land, to agriculture to provide sustainable agriculture and more to produce better food for the population. And we have schemes to use them. And we understand, we're gaining understanding of how controlling the thermal variable will very positively impact coral reef systems and apex predators such as sharks, who are basically expending so much energy searching for prey due to increased energy needs at higher temperatures, that their reproductive potential are decreasing as the ocean gets warmer and warmer. We also have multiple schemes of how to more efficiently capture energy using MEER-enabled infrastructures, and today Gregory will talk to you about later. And we also have means to stop or neutralize the methane that's coming out of Arctic and the permafrost, which we will not have time to go into today. And with that, I'd like to hand it back to the organizers. And welcome Ellie, who joined. She's another team member of ours.
Thank you so much for the introduction. It was very, very detailed. I do have a couple of questions, because we live in the Las Vegas area. There's a lot of solar plants that have mirrors to generate energy. Are these mirrors used to generate solar energy also, or is just like to reflect the sun? That's a question.
Yeah, I think those are concentrating solar thermal power plants. So those mirrors, they are mounted on tracking axes. So they more or less continuously point the reflected beam towards a central tower that captures or convert that light into heat. And that heat is then transported via a liquid salt transportation medium to make steam to drive turbines. That we understand very well and are very high efficiency. So concentrating solar thermal power during good hours have a higher efficiency than photovoltaics. And as I discussed, they also have less CO2 emission per kilowatt hour of produced electricity compared to photovoltaics. So they really should receive policy support to really further develop and bring the cost slightly down, and also because they actually have better climate impact compared to photovoltaics.
Thank you. Also, the question also is that, a lot of the investors, when they put money in or organizations, a lot of them at this present time in the world, they're looking for a return on investment. Let's say somebody says, here's $1 billion to fund this project. Is that purely a humanitarian effort, or there is some return for those people who put the money in?
What I can tell you is that if we received $1 billion funding, we have half a dozen ideas that can be patented, and if fully developed, those would enable substantial monetary return. But it's the ethics of our project to use the majority of the gains to better human civilization and to move past a capitalist-driven world and economy. We're happy to work with organizations and donors who share our vision, and we're happy to also have a compromise in how profits are used, but it would be against our vision and mission to really use this research and just to promote the same system that got us here.
Understood. Thank you so much for the explanation. So we can continue the discussion or presentation?
Yes, we can. So I will let Gregory, Rashida, and Ellie to decide the order of the presentation. Yeah.
I'm happy to share screen if you guys would want me to. Just something I didn't have open. Are you guys able to view? Oh, sorry. Okay.
Yes, we
Is
see it
everyone
now.
able to view it? Okay. So we're going to present a couple of our team's proposals as part of MEER reflection on our solutions in combating global warming and what EA highlighted on. So 2 of our members can't be here right now, but we're just going to jump straight to ecological modeling, and then I believe EA will touch on NOx valorization, but we'll have 4 components to our presentation. And this is just another repetition of what our mission and vision is and the goals that we're working towards with this project.
Okay, I'm not backstage anymore. So I'm Ellie Flynn, and I'm the spokesperson for ecological modeling. Would you mind going to the next slide? So as rising global temperatures alter atmospheric chemistry, nutrient cycles, and carbon fluxes, quantifying these disturbances and their effects on marine and terrestrial ecosystems is integral in proposing large-scale climate change solutions. So as we develop our MEER arrays, we really want to know the effect that they could have on natural systems in the ocean and on land. And we're also trying to quantify the effects of abiotic influences on these systems through an ecosystem model. And so our research aims to assess the effect of climate stressors, mainly temperature, moisture, and CO2 levels, and of the mitigation efforts that we're proposing at Project MEER Reflections, as I said, on terrestrial and aquatic ecosystems. And through a really extensive literature review, we noticed that the current mechanistic or the current ecosystem models, such as EWE, don't connect abiotic stressors to biotic interactions in modeling ecosystem health. So we would really like to connect these 2 ideas so we can properly model ecosystems. And our proposed mechanism is, or our proposed way of doing this is through a mechanistic model, which really focuses on like physical conditions and how they would affect biotic interactions, such as phenology and just species interactions. And our mitigation efforts prioritize ecosystem restoration through the stabilization of global physical conditions. And we can go to the next slide. So as I was saying, this is a main model that we've looked at, and it's called EcoPath with EcoSim, and it balances mass. And so you can kind of see, like, if you could click to the next. Yes, so it doesn't take into account abiotic things like energy or temperature or CO2 levels when it creates its model. And so we really want to take into account these things when we create our own mechanistic model so that we can properly model ecosystems. And could you click again, please? Yes, so that's pretty simply like what our goal is in ecosystem trophic modeling. And then if you could click again. So our model will help us find the results that we can attribute to a given variable, for example, temperature, and it will allow us to look at complex ecosystems and higher trophic levels versus just like single trophic levels. And as Ye was saying, we can like sort of observe the effects that climate stressors have on like apex predators and their like interactions with lower trophic levels and that kind of thing. And so that's pretty much all I have to say for ours.
Hello, just again, my name is Gregory Pan, and today I will be talking to you guys about how MEER wants to revolutionize the residential energy sector to be more sustainable using the energy demand vector concept. Next slide. And this graphic here shows our energy production history, and we can see that fossil fuel-based energy has increased in total generation over the last 60 years, while non-carbon energy has not increased in a significant manner. As our energy demand has grown, we have became more dependent on fossil fuel-based energy. Next slide. In addition to this, if we look at the residential energy consumption, which is the focus of our team, we see that the residential sector represents about 1/5 of the energy used worldwide. This means that we can increase our non-carbon energy generation by about 20% if we create a suitable residential energy infrastructure through the EDV. Next slide. So before we get into what the EDV is and how we are planning on using it, let's take a look at different photovoltaic efficiencies and how they have increased in history. We see that overall, the efficiency of photovoltaics and solar panels have increased to about 48%. And this requires multi-junction cells that are extremely difficult and expensive to fabricate, making scale up very challenging. Pursuing efficiency improvement as a key strategy can therefore be one of several explanations of why the growth in solar photovoltaics and other renewables is slower than the net growth in energy demand. Next slide. We see a similar plateauing in improvements of efficiency in the heat to electric conversion process using steam turbines. There has been, and there still is, a heavy R&D investment in the sector of fossil fuel power plants and their ailment. As you can see, over the past 50 years, there has only been a minimal increase, not even 5%. That's a less than 1% increase every 10 years. These efficiencies have not been keeping up with the demands as for aforementioned, and the trend suggests that investing in the improvement of these technologies isn't going to help solve the problem of higher energy demand. Next slide. And so if we look at the current conventional approach to generating energy, we see that we have a centralized location that is converted to electricity, which is lost, and a lot of energy is lost as heat, and then further transported to the residential areas where the energy is then reconverted into heat or other forms of energy. The EDV approach takes the energy lost as heat and uses it for thermal energy, which is a main component of a lot of residential homes. If we go to the next slide, we can illustrate the analytical power of the EDV concept using an example data set for several states in the US. Each of these points represents average data from a state. Larger circles represent states with larger populations. The X and Y coordinates of a point respectively represent the per capita energy consumption of space heating and AC cooling. The color of the circles encodes the average winter temperature of that state, or average summer temperature of that state. We see a clear correlation between the direction and magnitude of the energy demand vector with local climatic conditions. Notice that the range of the two axes are different. Quantitatively, the visualization shows that colder climates require more energy for achieving thermal homeostasis, leading to greater energy requirements. The main takeaway from energy point of view is that the EDV is highly location specific, suggesting that distributed one-step energy conversion technologies need to be tailored to local needs for maximal efficiency. Next slide. And here we have a follow-up analysis inspired by the previous EDV visualization and reveals insights about the average temperature preference of Americans. Here we plot the per capita AC cooling consumption against summer average temperatures, but plot per capita heating against average winter temperatures. The y-axis of the fractional energy usage of each individually. The normalization may serve to control for economic and cultural disparities across locations. Linear fits to the dataset intersects with the x-axis at around 20 degrees Celsius. At this ambient temperature, individuals devote less than 10% of their total residential consumption to thermal regulation, suggesting that the optimal temperature for humans in the United States is around 20 degrees Celsius or 68 degrees Fahrenheit. Next slide. And now here is a diagram showing the total US residential energy consumption. On the left side of the diagram, flowing towards the center, is our current energy generation and distribution for residential means. The overall height tells us how much primary energy is being consumed to produce the red portion, our national EDV. On the right, we have a much smaller total primary energy source because we removed the remote convergence step, eliminating losses in that process represented by the black bar at the bottom center. In the application of the EDV, we will be looking at making use of the abundant source of photon energy the sun provides, but the primary source of energy of the EDV can in principle be anything. And that is it.
Through this one, I could in principle go over, I will ask the host to see whether there's a time to discuss. Otherwise, we can also move on to Rashija. Yeah, maybe let's do Rashija's part first because that's quite important. The problem of ocean deacidification. Yes.
I am a part of the ocean deacidification team. So we all know that global warming is a critical issue facing humanity, but there are fundamental links between warming and ocean acidification that are often overlooked. Hundreds of years of anthropogenic carbon dioxide emissions have reduced seawater pH, increased dissolved carbon dioxide levels, and these conditions will exacerbate existential threats to marine species. So we want to target this knowledge gap by considering relative sensitivities to stressors within marine biology when targeting global warming. Our MEER-based infrastructure will enable carbon dioxide drawdown via a strategy of artificial ocean alkalinization or ocean liming. We aim to not only combat global temperature rise, but also restore marine ecosystems and maintain phytoplankton health. My two team members have been conducting in-depth research regarding the last 2 points. Today, I will talk about our proposed solutions specifically. So ocean liming is the dissolution of calcium oxide into calcium and bicarbonate ions. And here's the basic chemistry we're working with. We see from the ratios of the first equation that liming allows the sequestration of close to 1.7 moles of carbon for every 1 mole of calcium ion that we add to the ocean. Additionally, we see that lime dissolution is highly spontaneous. The second equation depicts the production of lime from calcium carbonate, whose common form is limestone. This process is endothermic at standard temperature and it releases carbon dioxide emissions. However, when the solar thermal energy from our MEERs drives this reaction as opposed to fossil fuel, it is much more energetically feasible for large-scale intervention. For our discrete calculations, we assumed a net flux of 11 petagrams of anthropogenic carbon input per year, which was the average of the period 2009 to 2018. To neutralize this annual release of carbon via liming intervention, we estimate needing around 50 gigatons of calcium carbonate or 30 gigatons of quicklime. This would suggest the current global annual production of quicklime to be increased by a factor of 66.7. Given this amount of calcium ion found in the global surface mix layer, which we take to be a depth of 100 meters or less, we predict a 0.134% annual change in its concentration for each year of liming. This small perturbation we expect to be localized and offset in the long term. In this schematic, we see the simplest version of our liming strategy where we mine limestone and power calcination with our MEERs. You can see that upon adding lime, a very rapid and selective acid-base reaction takes place, thus combating the acidification from anthropogenic carbon uptake. We also see an immediate benefit to marine species such as coral, who rely on these ions for their structure. Ocean liming is a geoengineering technology that has had limited research focus in the past. However, in assessing these various methods for CO2 drawdown, we find that other methods are not particularly feasible or kinetically favorable. We highlight direct air capture as costly both financially and energetically. This technology uses alkaline sorbents, which are readily available to capture carbon dioxide from ambient air. Our estimates suggest the energy demands are very high, in large part due to gas demixing, which is not spontaneous. To add perspective, this value is higher than the amount of energy the world uses annually, suggesting it may take decades to improve the process efficiency to be feasible. Mineral carbonation is yet another method that is cheaper and has relatively low energy requirements, but it's not as scalable due to limited resources. Ocean liming, on the other hand, has readily available calcium carbonate, and it is kinetically favorable because it harnesses the huge surface area of the ocean. Oceans are large enough in capacities to store the equivalent of carbon emissions sourced from fossil fuel reserves, and this is a requirement that's hard to find among other carbon sinks. We find it energetically favorable when calcination is driven by concentrated solar energy rather than fossil fuels, and it's also viable when implemented in conjunction with carbon capture and storage. However, we find none of these methods as presented to reduce atmospheric CO2 on the mass scale needed. To solve this issue, we propose using shellfish, which are composed of calcium carbonate as source material. This reduces the CO2 burden of limestone extraction and processing. Going back to the schematic, we see that it is an open loop system, which is not sustainable given the limited time at hand, because the ocean carbon content will increase over time, while the atmospheric CO2 levels likely stay constant and limestone reserves will become limited. Incorporating shellfish would enable a long-term cyclic strategy to produce renewably sourced lime that would close the carbon and calcium loops. Coupling liming with aquaculture increases calcification and leverages the higher primary productivity of oceans under CO2 fertilization. Additionally, we would valorize waste shell resources and promote food production. Here we also show the storage of the concentrated CO2 streams resulting from lime production. This happens through injection into materials like basalt rock or deep saline aquifers, followed by the burial of these materials. These may be buried as deep as 1 kilometer, where it could be stable for thousands of years. Another option is to use this highly pure CO2 as feedstock for fuel synthesis. We can make liquid hydrocarbon fuel for transport use by electrochemical reutilization of the 100% concentrated CO2. This process could also be powered by our MEERs and even take place at the same lime plant. We can see that our sources can balance with the sinks, enabling a circular carbon economy. There is one more element that we propose to maximize this intervention's impact on our planet as well as our civilization, and that is to incorporate residential heating, as Gregory discussed with urban built environment, into our strategy. Calcium oxide, the benefits are that it's highly soluble, but it is a bit wasteful because the reaction releases heat. And if we were to undergo hydration with water first to produce calcium hydroxide, which is still soluble, this would provide a lot of heat energy that could be that has the potential to fulfill residential space and water heating requirements as part of this entire calcium loop. And I believe the next 2 slides, Ye will be elaborating a little bit more than what I've been talking about. But
Thank you. Yeah, thank you.
Okay.
So basically here we're doing a thought experiment. So the thought experiment is, let's assume for a second that everybody transitioned to eating just seafood. And there's multiple reasons for doing that. One of which is that land-based agriculture is really devastating biodiversity on land and incurring soil loss and additional emissions of methane from the farming of cattle and goats and sheep. So here we make the assumption that somehow we moved or vastly expanded the production of bivalves, and that we obtained most of the protein and energy need for the whole world from such aquaculture production. So associated with this amount of clam and oyster meat, we have a lot of shell calcium carbonate produced in the process by the biology of these farms. And we can calculate that if we were to fulfill the nutrition this way, we would be able to sequester in this process of biogenic calcium carbonate formation roughly half of the CO2 emissions from year 2019. And this shell material, as Rashida mentioned, can be decomposed into the calcium oxide and the CO2 component by solar thermal calcination furnaces and plants. And this calcium oxide, when you do the hydration reaction, releases enough heat to provide basically the entire world's need for residential space heating. And coincidentally, the hot CO2 gas coming off from the shells at 800 or 900 degrees Celsius roughly has enough thermal energy content in it to heat enough water to power the entire world's hot water need. So the utilization of the chemical and physical forms of energy in this process could lead to an additional 9% reduction in total fossil fuel use. And this scheme together satisfies then several needs of our civilization. So the nutritional need, if we moved agriculture off land, that leads to about 6 gigaton reduction in greenhouse gas emissions, equivalent to CO2 emissions. And we sequester half of the emitted gas that we need to sequester if we either reutilize that or inject them into underground storage. And then we have the additional saving because we didn't burn fossil fuel to heat our buildings and our water. Next slide, please. So overall, this example shows that it's possible by putting together different parts of the puzzle in a coherent framework, we're able to drastically reduce current emissions by up to 75%. And if we believe with such expanded solar thermal infrastructure, we convert electrical production also to concentrating solar power, we would be in a very good spot of being able to, through the oyster and the clam farming process, perform a net drawdown at a rate of 5 gigaton CO2 equivalent per year. So I think that's most of the story we'd like to share, and I give it back to the host if there's questions from the audience and from you guys.
Thank you so much for the presentation. Hello?
Hello, yes, I can hear you. Can you hear me? Ellie, Gregory, you guys can hear me? Wave. Okay. Oh well, maybe in the meantime, let's Okay, Alice is coming back.
Thank you for the presentation, you guys. I think David's internet connection has froze on him. So I just want to say, wow, this is such an informative lesson that we haven't even heard in the news as much. And it's really, really exciting to see what innovations will come out of your research and your... Yes, and David's back with us.
Well, thank you for
Yes, sorry,
inviting.
I didn't know what happened. I have a couple of questions. You know, when you're using the shellfish, right, itself, is it, will you be harvesting the shellfish for dietary reasons and keep the shells? Or just might not make sense, a question, but just curious, you know?
Yeah, I think well, a lot of people that I've talked to, they're very enthusiastic about this idea because they're seafood lovers, myself included. So there's definitely a reason to make use of the protein. I don't believe in throwing away resources, and the protein is a high value resource. So we may not, all just eat seafood. We can also utilize that protein, say, to complement the diet of, say, chickens, so we have a little bit more varied diet. And so that's a thought experiment to show the potential of such approaches, but we're not really proposing that we actually exclusively only do this. So if we have multiple solutions in the toolkit that are unified by this glass manufacturing framework, then we can optimize for efficiency, for economics and material resource by taking different linear combinations of the different solutions in this self-consistent toolkit. And the other part of aquaculture in the ocean we didn't mention is that algae production is really useful, and it's a growing business, and there's opportunities there. And the reason is actually fundamental and scientific. So in a high CO2 world, a lot of macroalgae grow very quickly, and they maintain their high protein content. And that's not the case for land-based plants, including rice and wheat. So these crops tend to lose their protein contents because there's a limitation of fixed nitrogen resources on land. That's not the case for most of the marine primary producers. So there's an intrinsic scientific reason to move agriculture off land for our own sake, just getting more nutritious food, and also for the sake of land that's being increasingly encroached upon, and we're losing soil and losing space to rebuild forests and maintain or rebuild biodiversity on land. So there's multiple reasons why we should couple aquaculture with different aspects of our project, including, say, using floating MEER arrays as a floating platform for algae and other seafood farms.
Also, let's say if you wanted to build a pilot project, how much money do you need to build a pilot project? Because will be investors watching this, and said, because they always look for numbers. As if how much do you need for a pilot project for this thought experiment to make to see if it's successful?
Okay, so the mission of our project is to have the capability to implement this framework at scale starting in year 2030. I think that it's there's multiple lines of evidence pointing to on the order of 1 to 3 decades of time that we have left to make significant change. So we want to err on the side of caution and give ourselves 10 years to make this happen. And so we think to move to that stage, we need to start to develop the type of factories and the mills to do the full scaling up 3 to 4 years from now. So we give ourselves about 3 years to do dedicated fundamental material science R&D and simulations and calculations. And right now, we want to model this intense phase of R&D after the structure of our team, which currently has about 8 sub teams. Our project has 8 teams working on different aspects. You heard a few examples today. And so our cost estimate would be on the order of 60 million for 3 years of intensive R&D, beyond which time we should be thinking about scaling up.
Of R&D, okay. Okay, that's good. So thank you so much. If you have any other questions, Alice, have any
Yes.
questions?
I want to hear from Ellie, Gregory, and Rashija about their thoughts on this project and a short few sentence answer of what innovations you think can come out of this.
I can start. When I first joined this project, I had like the conventional climate change idea of, oh, we need to convert everything to wind and solar so that we don't have our Earth die. But then Ye does his presentation on how that is not the case, and if we do that, we will die. And I think that this project is a really, really eye-opening project that tells us that there are multiple ways to approach a problem, and there are some unforeseen consequences to certain solutions that we have to consider. And in addition to that, sorry, what was the second half of the question again?
Your thoughts on your project and what innovations do you want to see happen?
Oh yeah, so the innovations that my project is working on, we're working on some technologies that have yet to be patented, but we hope to implement these technologies to be used in the residential sector to lower the carbon emissions from energy use in the residential sector.
Thank you. Ellie? You have to unmute, or Rashija?
I can go. So I think something that was really eye-opening for me about this project was learning about how impactful temperature increases, especially on ecosystems, because growing up, learning in school, I always thought it was emissions, like carbon dioxide emissions. So that's been a really impactful thing for me to learn. And I think something that the trophic modeling team really hopes to accomplish is, again, to create our ecosystem model, which might not be like super impactful for like everyday people, but I think it will be a really amazing accomplishment in the academic world and in the science world. And the advancements that could come from that are ecosystem restorations. Obviously, right now we're losing a lot of corals and just other ecosystems and natural spaces, and these are things that I really hope to protect and that I feel a lot of passion for protecting. So that's kind of what.
Thank you for that. Yay, do you have any last parting word?
I think Rashija has yet to speak her mind.
Not too much to add. I agree with everything Ellie and Gregory said as well. But yeah, personally, coming into this project, I did not have much awareness beforehand of geoengineering technologies and ways to reverse climate change beyond what the common knowledge is, I think, of changing our lifestyles or converting from fossil fuel usage. And so now we're seeing the need to actually do an intervention. And even though the ocean deacidification, it's a really large scale proposal with many different innovative tools and technologies that it incorporates, I think the problem we have at hand is a grand problem, and it requires a solution just as well thought out and incorporating all these various loops that we've done. So I think starting with this project, there's lots of inspiration already coming, and there's ways we can continue to improve these methods and make them more innovative.
Thank you. Yay? Any?
Yeah, I actually have one last thought. So obviously, we are confronting multiple threats, and we need everybody on board. And it's also a priority of the project to educate the public and also form partnerships. And I think as the current members, mature, become competent scientists, researchers, and inventors on their own right, we are moving toward a stage where we can expand network and have just the current members becoming mentors and to teach younger students in different parts of the world. So we're looking also forward to testing different models of education and in STEM. Because right now it's almost a privilege to go to college and receive higher education, and that shouldn't be the case. And that's part of the reason why we're having debates about whether climate change is still real or not. So we should leverage the opportunity of COVID and moving most things online to think of ways to expand education, higher ed, across border, across globe, outside of these ivory towers. So that's our one of our mission as well that we like to pursue. So if you are an educator, you're interested in learning about climate change or doing outreach, please reach us, and we'll be more than happy to assist and participate in your efforts as well. And thanks to Alice and David for the invitation. And yeah.
Thank you, everyone. You can rewatch
yes, you
this
guys,
broadcast.
thank you so much for this. Really excited about your project and your the young people will help bring the solutions for the future of our planet. Also, one last thing, because Indigenous people, this event is hosted by Indigenous people, which people call Native Americans or original peoples. How can Indigenous people participate in such a project? Besides because they protect 80% of the Earth's biodiversity, also govern 25% of the Earth's land and protect 80% of the Earth's forests. And there's a lot of island nations that also are also being potentially wiped out by the sea level rise. So how can they participate in such a project?
I think, first of all, the Indigenous people, they have a great depth of knowledge and the connection with the ecosystem because their livelihood depends on a healthy ecosystem. So for decades, they have been fighting, just with their kayaks against tankers in Australia and the New Zealand. And so, so what we would like to help with is to also help them really understand the complexity of the system, and that at this point we need to be united and smart about which solution that we support and we go to. And but of course we also need the majority. It will not only impact the most vulnerable, it will also very soon come to a place near you, regardless of how privileged and shielded you think you might be. So it's a message also for the heads of states and also the billionaires. Do not believe that your wealth will be able to protect you or your children for much longer. And we're all in this together. And in the end, I want to say that money or wealth really means nothing. Like people on the front lines, the Indigenous people who are suffering, many of them, I guarantee, are having a more meaningful life than those of you who are pulling the strings of empires. And in the end, you need to ask yourself as a human being, what's the meaning of your life? What's meaningful? Yeah, so I think with that, I'd like to also thank all the students that have participated in the project, and we like to see more people joining.
Any closing words about Indigenous from the students themselves? Some share ideas how they can work together with them.
I personally believe that, I agree with many of Ya's sentiments about how, the indigenous people have been fighting the good fight, I guess, and how, we have to do our best to support them, not really the other way around. And so, hopefully we can work together with them to help bring awareness to the general public and get some meaningful change to really save the environment and save the world.
I think also because of the online nature of everything going on, MEER Reflections might be able to provide resources such as presentations that we've presented, or maybe like pre-recorded presentations to Indigenous people. I know that we are all members, at least the team is, of college universities, and a lot of them, as my college does, has centers for Indigenous people that we could maybe distribute materials to or invite them to our conferences. But yeah, other than that, I think reading is really important. Like reading literature on climate change could be a really good way to like stay educated, and also voting is really important. So I don't know, like just staying knowledgeable, I guess.
Anyone else want to say anything? So so we would like to keep in touch because it's a unified effort to be able to restore the climate, and not only the climate, our ecosystems and so many other things that are being threatened. There's a threat of the sixth mass extinction and so many other things. And it's a unified effort is because, yes, one solution is not the overall solution, because we need multiple solutions for this to be combined together. Like example, like Indigenous people were defunding the banks, trying to defund the banks from supporting or supporting with capital these fossil fuel companies. That's one example. The other example is to try to stop the pipelines or the destruction of the rainforest. That is a combined effort with these solutions that need to come together, is because by supporting each other, we will resolve this issue. But I don't think it's a single solution that we can solve the issue of climate change. Also, climate change is really interconnected with other things like poverty. Example, if the people are extremely poor, they would not care about the climate, or other issues. There's so many issues that are connected with, including, like example, indigenous rights is connected with the climate change. Is because that allows the fossil fuel companies to go into the Amazon and destroy for fossil fuel or other things. So all these things are interconnected by one another, and by helping each other, I think we will find the solutions.
Yes, let's hope so. Yep.
Thank you, everyone. This broadcast can be watched on Facebook, Live Hope Festival. And we look forward to working with you guys in the future.
Yeah,
Thank
thanks
you
again for the invitation, and please keep in touch, and also help us getting connected with other solutions and frameworks and organizations and the indigenous communities.
Yes, thank